to one and all. This is Bhavsar Sonani, Assistant Professor, Department of Chemistry, Google Education Society's Arts, Commerce and Science College, Jawar, District Palkar. Dear friends, as far as concerned with the quantum chemistry, in the semester 6, we have completed most of the topic of quantum chemistry or the basics of quantum chemistry in the semester 6 of TYPSC chemistry. Dear friends, if you remember about the previous lectures, we have discussed about the distinguishing between classical mechanics and the quantum mechanics. Also, we discussed about how the quantum mechanics is helpful in order to explain the phenomenon like black body radiation, photoelectric effect, or the Compton effect. At the same time, in the last lecture, we discussed about the de Broglie's wave equation and the experimental verification of de Broglie wave equation. This is also called as de Broglie's wavelength. Dear friends, today in this part of the video, now we are going to discuss about the uncertainty principle given by the Werner Heisenberg. That's why it is also called as the Heisenberg uncertainty principle. Dear friends, if you will discuss about the Heisenberg uncertainty principle, actually this principle is given by the Werner Heisenberg and which is known as the Heisenberg uncertainty principle. So according to this principle is applicable to the subatomic particles like electrons, which are always in a state of motion. And in the last part we discussed about the DL nature of the subatomic particles like electron. Definitely they show the wave nature and the particle nature, and because of the wave nature they also show the other phenomena known as the uncertainty in its position or the uncertainty in its momentum. So Werner Heisenberg proposed a principle which came to be known as the Heisenberg uncertainty principle, and according to him it is impossible to determine the position and the momentum of a moving microscopic particle like electron with absolute accuracy simultaneously. It means that we cannot determine the position and the momentum of moving particle, microscopic moving particle simultaneously. It means that either we can define the position or the momentum at a time whenever the particle is in motion or the particle is moving or the microscopic particle is moving. Generally this is more applicable to the particles like electron or the subatomic particles or the microscopic particles. Suppose here we will try to define this, or we will try to explain this with the help of this equation. Suppose delta x is the uncertainty in the determination of position of this microscopic particle like electron. Uncertainty, remember that delta x is the uncertainty. If the uncertainty is more, certainty will be less, and if the uncertainty is less, then the certainty will be more. Similarly, delta p is the uncertainty in the determination of momentum of microscopic particle. Then according to the Heisenberg uncertainty principle, that delta x into delta p is greater than or equal to h upon 4 phi. But you know very well that in the last lecture we discussed about the momentum, and here momentum is the multiplication of mass into velocity. And if you put this value for the mass into velocity for the momentum in this equation number 1, so that will be written as it is the microscopic particle. It means its mass is constant. That's why delta x into delta p is greater than or equal to h upon 4 pi m. Here remember again, delta x is the uncertainty in its position, and delta phi, here delta p is the uncertainty in its momentum. But now this momentum is replaced by its velocity, so delta v here is uncertainty in its velocity. So this above equation is more satisfied when it is applied for the particle like electron, or whenever it is applicable for the particle like having very low mass or the small mass like electron. For example, suppose here we will discuss about the electron, then the mass of electron is 9.109 into 10 raised to minus 31 kg. So therefore, if you put this value in this equation, that is mass, because this S is the Planck constant here, pi is having 3.14, and m is the mass of electron, which is 9.109 into 10 raised to minus 31. If you put all these values, then the multiplication or the product of uncertainty in its position delta x and the uncertainty in its velocity delta v can be calculated. Simply it is 5.792 into 10 raised to minus 5. If you look at this value, definitely this value is considerable. This value is found to be very high, or it is high. So here we found the product of uncertainty in its position and the velocity is very high. Here uncertainty is very high. It means that the certainty is very less or very low. This is for the particles like electron, means this is for the microscopic particles. So here for the microscopic particle we are getting certainty is less, certainty is very low. It means that similarly if we will apply this equation for the another particle like a ball having considerable mass 0.01 kg, so here we will get the multiplication or the product of their uncertainty in its position and the velocity 5.27 into 10 raised to minus 31. So here the product of this uncertainty is very low because it is 10 raised to minus 31. This is negligible value. So here product of uncertainty is low. It means that the certainty is very high. Here certainty is very high, and in the earlier case in the microscopic particles certainty is very less. So we cannot define the exact here in case of microscopic particle. So the conclusion can be drawn from these two examples that the Heisenberg reached to the conclusion that the particles like electron has no definite path. Here we cannot define the particular path for the microscopic particle around the nucleus because of its dual nature. It means it shows the particle nature as well as wave nature. That's why we cannot define the correct position or the correct or the definite path of the moving electron around the nucleus because of its very negligible mass or because of its dual character like particle and the mass or particle and the wave character. Dear friends, based upon the same, here we can define the distinguishing between the different types of the waves like matter waves and the electromagnetic waves or the radiations. So if we'll talk about the matter waves, then these are the waves inherently associated with the particles of matter. So these are constituted by means of particles. These waves consist particles. So while the electromagnetic waves of energy associated with the electric and the magnetic field. So these waves consist electric and the magnetic field. Again, the matter waves have very less speed. So definitely if you compare the speed, then the speed of matter waves is very less or negligible, while the electromagnetic radiations of the waves travel with the speed of light, that is 3 into 10 raised to 8 meter per second. Again, the matter waves do not travel in the vacuum. So here the matter waves are not able to travel or to pass into the vacuum, while the electromagnetic radiations of the waves can travel in the vacuum also. So again, the wavelength of matter waves are very small as compared to electromagnetic radiation, while the wavelength of electromagnetic radiation is observed in the form of range that we called it as the electromagnetic spectrum, and this electromagnetic spectrum has wide range of their wavelength because it almost consists many types of electromagnetic radiation. So these are some points regarding with the distinguishing between matter waves, which consist of the particles, and the electromagnetic waves, which consist of or which is associated with electric and the magnetic field, or it consists of that it shows the dual nature. So these are most important part of the quantum chemistry. After this, we will look at the some operator or the another concept of operator in the quantum chemistry or the quantum mechanics, that we will look in the next part of the video. Thank you. Thank you very much.